work done in a reversible isothermal expansion. Derive an expression for the work done in a reversible isothermal expansion in terms of volume and pressure. So the first thing that must come here now is we need to go through the first law of thermodynamics. The first law of thermodynamics, which is the first law, states that the algebraic sum of heat input into a system must be equals to the sum of the heat output by the system. So from that expression you have it that from the first law of thermodynamics, the heat input, the Q, equals to internal energy of the system plus the work done, the W. So at this point all I need to do is in an isothermal expansion or isothermal process, change in temperature is always equals to 0. That means temperature is constant in an isothermal expansion, and the U itself is what? CV, molar heat capacity at constant volume multiplied by the T. So if the T equals to 0, that means the U, the internal energy of the system, is going to be what? 0. So at that point we are left with the Q equals to the work. And for an isothermal expansion, the Q and the work still gives the work. The work now will be P dV, which is the product of the pressure multiplied by the change in volume. Now if we have an increasing volume of the gas, from, let's say, the volume of the gas increases from V1 to V2, which is initially, then all I need to do is to integrate what I have here. I will integrate the left hand side and I will integrate the right hand side. So if I bring the integral sign, integrating change in work, I can just write it as the work, a small increment over integrating P dV as we go from V1, which is the lower boundary, to V2, which is the upper boundary. Now recall that for an ideal gas, equation of an ideal gas is PV equals to nRT. Now if you look at this equation, this integral here, we can't integrate pressure with respect to volume, so I need to put in the value of P from this ideal gas equation. So make P the subject of formula here. P becomes nRT over V. Call this equation 2. Let me label this as my 1. So all I need to do is to put these two back into equation 1. So if you integrate the work, it's going to give us the work done here. It will now be integral, as I move from V1 to V2, of, in place of P now I'll replace it with nRT over V. So I have nRT over V with what? The V. So work done here will now be integral, as I go from V1 to V2, bring of nRT over V dV. So all I need to do now is to bring out the nRT, because I cannot integrate volume with respect to that. So that gives the work done, W, when I bring out the constant nRT integral as I go from V1 to V2. What I'm left with is 1 over V with respect to V, which is the V. So this will now be work done in the isothermal expansion, which will be nRT. If you integrate 1 over V, standard integral, 1 over X we give ln X, then 1 over V now we give ln V, but as you go from what? The lower boundary V1 to V2. Now this integral now, ln V takes ln V now we take the value of the upper limit and the lower limit. So I can have it as ln V, but as we go from V1 to V2. So all I need here is ln V, take the value of the upper limit and V also take the value of the lower limit. And if you look at this sign is a determinant sign, which is modulus, it means negative. So from the law of logarithm, if you have W equals to N RT, now V here becomes V2. You have lane V2, that is this lane V has taken the value of the upper limit minus lane V1, the V has also taken the value of the lower limit. So at this point you have log work done equals to N RT. This is subtraction in logarithm. If you have subtraction between two logarithms, we divide. So this will give lane V2 over V1. Now this is the work done in the isothermal expansion in terms of volume. What we have left is V2 over V1, but we are asked to look for the work done in terms of volume and in terms of pressure. So for pressure now, you have to recall that Boyle's law states that you are left with P1 V1 equals to P2 V2. So how can I rearrange this? What we have in this previous equation is V2 over V1. So if I put V2 here and I divide it by V1, it will be equals to what? What should I place at the numerator and what should be at the denominator? So for the numerator now, for me to get P1 and V1 back, I need to place P1 here. So that when I cross multiply, that will give that. For the denominator, I need to place P2 here. When I cross multiply, that will give V2 over P2 V2. So that means V2 over V1 in this previous equation 3 could also be replaced as P1 over P2. Once you replace that for this equation, it becomes the work done in the reversible isothermal expansion in terms of pressure, while this first one is in terms of volume. So I'll put this P1 over P2 back to this last equation, so we can have the work done equals to nRT lane, then you have it as P1 over P2. Now this is the work done in the reversible isothermal expansion in terms of pressure. So you have in terms of, this is in terms of volume, while this is in terms of pressure. Now what we consider so far is when we are dealing with n mole of a gas. So if n equals to 1, if you are dealing with 1 mole of a gas, so the work done in terms of pressure could now be RT lane P1 over P2, and in terms of volume also it could be RT lane V2 over V1, and that gives the equation of a reversible isothermal expansion, work done in an isothermal expansion, in terms of pressure and volume.